For our last talk, we'll have David talking about skolemization and models of B sigma n and not I sigma n.
Thank you for the introduction and
thank you for the invitation.
It's been a lovely meeting so far, hasn't it? Well, now you're stuck with me. And this topic, which it doesn't sound too appetizing, right? I'm sorry, I didn't think of a better title, but I promise it's actually some interesting stuff. Now, this is ongoing work, so it's not totally complete. Sorry if it's a little rough around the edges in some places. And it's joint work with the displayed people, C.T. Chong, Li Wei, Lawrence Wang, and Yang Yue, all of the National University of Singapore. So, skolemization and models of B sigma n plus not I sigma n. So, that's a false axiom, just what most people would say, but it's something we like to play with a lot. And sometimes you get a proof with a cut in it, for example. And this type of thing turns out to be pretty useful. Well, later on. So, to begin, I assume you all know what skolemization is normally. You have two quantifiers, and you make it into a function. This is what it would look like in a model of arithmetic, which is what we're working with here. So the thing you'll notice is that the function you get would be a second order thing, or a thing of higher type, depending on your point of view. It's not something you normally want to tangle with when you're talking about first order arithmetic, or second order arithmetic for that matter. And if you want to know see why, I think a question many people have thought about and studied and so on is, how do you extend it to higher n? And well, there are two obvious ways, both well trod over. One is you pair up these quantifiers from the left, and you get something that way, or you pair up the quantifiers from the right, and you do something that way. One of them will give you a certain set of functions which take each other as their output as input. The other way will give you these functions of higher type. Both are pretty sketchy when you're trying to do first order arithmetic, but certainly the ones of higher type are more so. I suppose in these higher type systems you could do that, but I don't know any way of translating that back to something about first order. So question mark just means it's food for thought. I know people have thought about that stuff before. Interestingly, at least to me, is that what we're actually going to do is use those functions of higher type. But in this, in models of not I sigma n, that's actually going to work sort of in a funny way. And I guess alternative approaches, I haven't said to what, but alternative approaches to rearranging arithmetical formulae. You can use Post's theorem to relativize to zero something jump and get, therefore, a simpler formula for something in the second order part. You can use the limit lemma. A delta n set is the limit of limits of arithmetic. Everyone knows that. And yeah, the approach we use here definitely uses these functions of higher type, but also in a funny way that I confess I don't really understand yet. It also resembles, within the proofs, which I'm actually going to rely on the hard ones here, it actually uses limits of limits, so to speak, but I'll see if I can describe what I mean by that. Anyway, that's what skolemization is. So I told you these were going to be models of B sigma n plus not I sigma n, plus the exponential function being total. Sometimes we forget to write that, but it's necessary when n equals 1. So let's see. I've put 3 things here that are true of models of B sigma n plus not I sigma n. The first 2 can be taken, if you like, as definitions of, let's see, B sigma n and I sigma n respectively. So B sigma n is the same as, well, let's say B sigma 2. Let's start with 1. B sigma 1 is the same as saying that every computable set is regular, also called by a few different names. Amenable, piecewise coded. It just means every individual makes sense within the model. And then B sigma 2 is the same for delta 2 sets and so on and so on. And then, yeah, I sigma n, when n equals 1, is the same as saying that the halting problem is regular in the same sense. These are provable equivalences. I guess you need the exponential function, sorry for its omission. And then there's the third thing. I think we've seen something like this. Antonio Montalban's talk. There's this corresponding notion from alpha recursion theory of an admissible ordinal. And they have something like this as well. So what this is that, what this says is that there's a proper sigma n initial segment, call it I, necessarily a proper cut. That is, it has no maximum element, but it also isn't cofinal, which is sigma 1 to sigma n definable. And there's a function from that I, cofinal, increasing into n. Well, that's sort of an exotic thing if you're used to standard models, but in a non-standard model, it's only definable, so it's perfectly fine to have around, and it can be useful. And that is going to be, I called it F, later I'll call it G. These I and G are going to be really central to what we're talking about. So, first I'm going to give you an opinion. That when we're working with I sigma n plus not B sigma n plus 1, or the other way, P sigma n plus not I sigma n, I'm going to claim right now that it's always easier just to assume n equals 1. And that's because n picking around makes everything more confusing. Having complicated formulae makes everything more confusing. And at least in the case of first order models, you can always add 0 n minus 1 jump to get a model of the corresponding B sigma 1 plus not I sigma 1 and work there. I guess it's just an opinion, but I hold it fairly strongly. Now, anticipating an objection that maybe this wouldn't work for second order models, you can see I saved a lot of time in LaTeX by handwriting this diagram. Sorry for the chicken scratches, but if you have a second order model, what does this prove? It proves that you just, instead of adding 0 to the n minus 1 jump, you take some n relative to which I sigma n didn't hold. There has to be one, a particular set A in a second order part. And you just add its n minus 1 jump. The objection would be maybe there's another B also in the second order part that will cause some conflict and break B sigma 1. And then what this diagram shows is that there should be an A plus B down here somewhere, I suppose. If you started with A, you went to AN plus 1, and you're worried about AN minus 1 rather, AN minus 1 plus B. Then you look at B plus A, and its n minus 1 jump is also here. By B sigma n, its n minus 1 jump is a model of B sigma 1. That's all. So there is no problem. I don't know what we're using here, some likely formalized version of Post's theorem. That's all. It should work, yeah, up to exactly this level, B sigma n. It'll break down after that, I suppose. And I guess the other objection we can anticipate is that, oh no, what if you can't go back? What if the stuff you've proved in this new model is not applicable to the original model? I say, once you have something that you found in this new model above a n-1 jump, or 0 n-1 jump, you can then apply the basic jump inversion theorem of Friedberg n-1 times and get something back down there with the corresponding number of, well, the corresponding quantifier complexity added back in. That will be, again, a lightly formalized version of that theorem in this axiom system. I promise everything works out okay. It's really a very, the formalization is a sort of a formality. Everything just goes through. All right. So that's good. We've eliminated n. We don't have to worry about it anymore. Now you'll remember there was a function before I was calling I, or I was calling f from a proper cut I, cofinally into the model. Now I'm calling it g. Sorry about that. Now, once we have m being a model of b sigma 1 plus not I sigma 1, I claim that g is, if it's a model of RCA 0 star, then g is in the model. If it's just a first order model, then I guess I'm claiming that g is delta 1. Why? Well, one possible argument is that g being sigma 1, enumerated in increasing order, is therefore necessarily computable. And furthermore, everything delta 1 in g is computable. It only uses a finite initial segment of that diagram. And I'll just emphasize now, it is important that g is viewed as a graph and not as a machine for spitting out results from inputs, but I wouldn't give you the same thing. G really is a set of ordered pairs, and you look at the diagram. Another possible proof of this would be instead of doing that, you can take a sort of syntactic view of these formulae which define it. And then you can get one of the next quantifier class value. But there's a small fib here. If I'm droning too much, maybe you don't see it. I'll try and liven myself up. Slight fib here is that when we're going relative to an oracle, delta 0 might not really be the same thing as we want it to be. It starts to depend on your definitions. It might be more proper to say it's pi n, it's a difference of pi n sets. When you slow it down, you're going to take some minimization. Although delta 0 is closed under that type of operation, relative to an oracle, it starts to depend on what you actually want it. Sigma 0, pi 0. Anyway, either of those methods will work with some care. So that's good. It means we can talk about G as if it were in the model, because it is. And we can put G into or the diagram of G into our formula with no cost in terms of quantifier. So here is a first example of how you might start Skolemizing a two-quantifier formula, while using this proper cut. It's not possible to apologize for a few rows of symbols. It's just the way it is. But you can see what it comes down to for the first line, at least, is that because G is a cofinal function, every x is below some value of G. So that means every x is below G of I for some I. Then you apply B sigma 1 and you can switch some of those quantifiers around. That's what this y0 is. It's exactly what b sigma 1 gives you from its basic statement. And then the third line is applying that reasoning again, that y0 is also below some value of g. Therefore, there exists a j in the domain, which can be used instead. And the last line is some kind of Skolemization, but it's not a very good one because it's just definable. It's hard to write it as a formula that's usable for anything. In other words, it's not in the model. And one more thing about this slide I should probably emphasize is that you might think you could go on upwards, pi 3, pi 4, and simplify them all this way. But it's at least not obvious what you should be able to, because there's an important use of b sigma, in this case, b sigma 1. And once you start having things like this inside and you have another quantifier on the outside, it's not clear how to use b sigma 1 to perform those quantifier exchanges to get this done. So the thing I was complaining about is that f is not in the model, and this is where we can actually use a nice theorem. It's called the coding lemma of Chong and Mourad. Chong has been here in the flesh this week, and Mourad I've seen at least once in the chat. So hello if you're out there. And with apologies to both of them, neither of these two forms I'm listing are really the original form, but they're equivalent.
There's also another Mourad in the chat. That might be a different one.
Oh no, sorry. Maybe delete that yeah, well, anyway, with apologies, neither of these is quite the original version of the theorem, but they're equivalent. And I mean that both in a really informal sense, that you can use them to derive each other. They're also formally equivalent to the theorem, and also to b sigma 1 or b sigma n over the next theory, I sigma n minus 1, let's say. So what are they? One is that any sigma 1 partial function from a finite set to a finite set, finite according to the model, can be extended to a total one. That's really useful, and I'll show you one use in a moment. A second one is this separation principle. So we're not going to use this form of it, I don't think, today, but I threw it in because there was some discussion earlier this week about separation principles, separation axioms, if you want to call it that, being all, well, let's see, weak Koenig's lemma and ATR not at least. And arguably, the other ones, like the so-called big five, can be characterized that way. So the point here is that it's not just those, b sigma n also can, just in this weird finite way. And if you really look into it, it's funny, b sigma 1 does look like compactness. A lot of characterizations are some kind of compactness there. Even the basic axiom of it looks a bit like the open cover finite subcover thing. It's strange. Anyway, that's the only reason we have form 2 right now. I guess one funny thing about form 1 that has nothing to do with the matter at hand, but it's kind of fun, is that it suggests another proof of the coding lemma. I'm thinking specifically of the case where the domain of f is a proper cut or an initial segment. You can get a proof of it that actually looks a lot like Slayman's proof of the equivalence of b sigma n and I delta n. It's kind of funny when you put them beside each other. Consider it a riddle if you like. if you don't like the talk, you can try and put these proofs beside each other and see where the joke is. Anyway. Moving on. The coding lemma, that's right. We were looking at the coding lemma, and we want a way to use it. So that's where our skolemization was just a moment ago. And the nice thing about the function f is that it is itself sigma 1 definable, which means it's sigma 1 definable and its domain is sigma 1, so it can be extended by the coding lemma to something that isn't sigma 1 definable, but is actually in the model. The only problem is that it's actually overshooting the mark a bit. That's okay. We have the fact that everything in the domain should map to something also in the same domain and satisfy the formula. And this is how I would write it. We talked about finite types. I sub 1 is just supposed to mean exactly this. It's a function from some bigger set, but within the intended domain, it behaves the way it's supposed to. And in general, you can define higher types in the same way. So these types are intended to capture sort of all the end to end to end to end to end. These things that should be uncountable and worse than uncountable, but within these finite domains and ranges. So the total number of these should be at most a power of 8, which in any case is going to be finite, as long as n is a standard number. All right. Now here's a theorem, a sort of normal form for formula, which is something I'm not going to prove. I would like to. I stayed up late trying to find a version of the proof that was suitable for putting on a slide, but I don't have one right now. I don't know if I should apologize for that or say you're welcome. It would, yeah, needs a bit more digestion before I can really make it slick. But anyway, that's the theorem. And it doesn't look like much, but it does have applications. And we're finding more, but here's one. This group at Singapore has been interested in these pigeonhole principles. How do we get into that? Well, at least some of us were doing something with randomness, and the first order part of that turned out to have something to do with pigeonhole principles from big numbers to small numbers for definable injections. And that's one of the ways we got into this particular question, but yeah, here's an application. If we suppose we have a definable injection from b squared to b, then the definition of the definable function takes this form from the previous slide. And then because everything here is bounded, x, y are bounded in this case by b squared and b, this thing is bounded. I haven't said how the IMs are coded up, and I don't really intend to. Someone told me coding is bad. We're being strict about it, so I won't tell you how it's coded. But anyway, the point is that total number of things in that type IM is no more than a to the a to the a to the a. And the total number of possible i's is no more than a for this fixed a that we fixed a few slides ago, and the total number of things satisfying a particular relation like that should be it should be a subset of the actual true function, the true injection. Which means the true injection has domain, has range, no more than b. The size is this size, at most, this size times that size, making this, which is true only for b smaller than the displayed number. Therefore, almost every b doesn't have such an injection. And you can play with this bookkeeping a number of ways. For example, it gives an alternative proof of a very recent theorem of Leszek and friends. Sorry, I've lost a parenthesis somehow. Their proof used some model theoretic techniques having to do with automorphisms. It could be that somehow hidden in that theorem you get the same reasoning somehow, but I have not been able to detect it. So let's call, well, on the face of it, it's definitely an alternative proof. And if you want other applications of this, Lawrence has come up with quite a few. But it seems we're going to end early. I'm almost done. I don't think anyone minds. One last thing I'll point out is that n should not be before 1. In contradiction to what I claimed earlier, we have a very specific thing that happens in the previous proof here, which was the use of the coding lemma to reduce some kind of definable set to a set that's coded in the model, an M-finite set. Now, the complexity of that phi has something to do with the n that you could get rid of. And you can view this elimination of that phi and making it into a coded set as a sort of quantifier elimination. But when you make n equal 1 and you relativize to 0 to the n minus 1, most of that information goes away. And just inverting the jump doesn't have any obvious way of breaking it down. Anyway, thank you very much. So, yeah, I'll emphasize that, again, this is ongoing work, it's joint work, and much credit is due to these co-authors, especially Lauren.
All right, does anybody have any questions?
I just had a quick one about that last result, because you had the system, but that's just for your proof, that's not the system they used originally, or is it?
Which is
The B negation I sigma 1.
oh yeah, this is, I mean, they use B sigma n plus negation I sigma n.
Oh yeah, so they use the same.
Yeah. I was just forcing my philosophy on them. It's not their idea. They do it the right way.
Any other questions? All right, if not, let's thank the speaker one more time.
So I guess David asked me to thank the organizers. So
Andreas asked me to ask Peter to thank the organizers.
Let's thank the organizers.
Adrian. Certainly Dennis is online. Ludovic, who am I missing? Andy, of course. So, did I get everybody? Okay, well, thank you guys for a great meeting on this.
It's a pleasure to know you all. Thanks
And if you guys can make me visible for a second, I just